So there's a number of different energy units which you'll have to become familiar with in this chapter. First and foremost is the joule, and we can sort of deduce what the units of a joule are from the equation for kinetic energy. So kinetic energy is equal to 1/2 times the mass times the velocity squared, and the velocity needs to be measured in meters per second, and the mass needs to be in kilograms. And so if we're just looking at units, not the equation, right? I have the mass, which is in kilograms, and I have the velocity, so this is m, right? This is going to be v squared, so it's going to be meters per second, like this, and I'm going to square it. What you end up with is a kilogram times a meter squared per second squared. So this is what we know as a joule. So a joule of energy is a kilogram meter squared per second squared. A joule is essentially, the energy required to move a 1 kilogram object a velocity of 1 meter per second squared. Now, there's other ways that this could be related, like you can calculate the energy. Another really important unit which is related is the watt. So W, right? Oh, sorry, I'll go back. And you've probably heard of things like kilowatt hours, which is down here, right? But a watt is actually a unit of rate. It's how fast the joules are being consumed. So it's actually a joule per second. It's the rate at which energy is being consumed. So when you have, for example, a 100-watt light bulb, then what you're actually saying is that light bulb is consuming 100 joules per second. Now, another common related unit is known as the kilowatt hour. So let's break down what that actually means. So a kilowatt, right? So a watt, oh gosh, I don't know what keeps doing that. A watt is equal to a joule per second. So a kilowatt would be 1,000 joules per second. And an hour is 3,600 seconds. So 1 hour, right? There's 60 minutes in an hour and 60 seconds in a minute, and that's going to be 3,600 seconds. So a kilowatt hour is 1,000 joules per second for an hour, right? So that's going to be 3,600 seconds. And so these will cancel out, and then I'll end up with 3.6 times 10 to the 6th joules. So a kilowatt hour is just another expression of the unit joule, and it's an expression of how much energy you will use, right, in an hour, basically. So if you're at a 2 kilowatt hour, then you'll be using 7.2 times 10 to the 6 joules in an hour. So we've already seen that the joule is the energy, or actually the kinetic energy, right, of a 1 kilogram object moving a meter per second. There's another physics unit. It's the unit of force, and we can say something like F is equal to m times a. And then we can break that down as kilograms, and acceleration is the meters per second squared. It's how much faster an object goes every second, basically. I learned it as a meter per second. So it's the velocity change per second. Now, but this is known as the unit as a Newton, like Isaac. And it's abbreviated N. So if you take a Newton, and I'm going to give this the term work, W, because this will end up being our work. If we can take a force and multiply it times a distance, right, then what that ends up being is that the force has a unit of a Newton, which is a kilogram meter per second, and the distance would be in meters. So this also comes out to be equal to a joule. So work units, kinetic energy units, are all in units of joules, and it's a consistent set of units is what we'd say. And this is how you would relate how much work energy, how many joules it took, say, to move a car as you're pushing the car. You would take the force that you put into the car times the distance that you moved the car. And then if you did it all in meters and all that kind of stuff in kilograms, you could calculate the energy in joules that it took to move that car. Now, having said that, another important unit is the calorie. And the calorie was defined far, far, far before the SI system was defined. And really, it was the energy required to raise the temperature of 1 gram of water 1 degree Celsius. Okay, so imagine you have a little cube, right? It's a centimeter on a side, so a cubic centimeter. This would be 1 milliliter. And you heated it up with a little flame, right? And it weighs 1 gram. Okay, so 1 gram, if you raise its temperature 1 degree Celsius, that energy, this energy is 1 joule, or 1 calorie, sorry. And this is actually a lowercase c. The case on this one is important. So if you had 10 grams of water and you wanted to raise the temperature 1 degree Celsius, it would take 10 calories. So this is all proportional to each other. And in fact, it fits in an equation that looks like this. If we think of the heat energy, and I'll talk more about this in a bit, but I want to make sure there's a tie here. Heat energy is usually given the symbol Q, and work, like I said, is given the symbol W. But heat energy, Q, can be related to the mass times something called the specific heat times the change in temperature. Okay, and this was an equation that was developed around the same time as the unit of the calorie. Because what they were doing is actually taking masses of water, right, and trying to raise their temperature, and they would see how much energy that would take, and this is where this equation comes in. I'll break this equation down and we'll do problems with it later. So a calorie, though, turns out to be, in modern terms, 4.184 joules. And then we have the dietary calorie. So the dietary calorie is given an uppercase C. And that's what you see on a packaging of food, for example. When you get a candy bar and it says it's 180 calories, that's an uppercase C, or a dietary calorie. It's actually, if it's 150 like calories, right, dietary calories, it's 150,000 normal calories. Okay, so a dietary calorie is a much larger unit than a sort of regular energy calorie. I've talked about a watt, right? And then I've talked about a kilowatt hour being 3.6 times 10 to the 6 joules. So when I was younger, I used to play a lot of chess, and I used to always read these stories about the old chess masters and their brains exploding, and them people dying playing chess because they were using so much energy in their brain. And anyways, a couple of years back, an article came out by Gizmodo, and they were trying to figure out whether or not your brain used more energy when you thought hard. And the article is actually, does your brain burn more calories when you think hard? And it's from 2018. So if you want to look it up, that's what you would look up. But in the article, what they say is, and I'll let you read the article to find out what the answer is, but your brain uses about 400 calories per day. Okay, so 2,000 calorie metabolism, about 20% of that is used just to keep your brain going. Your brain uses a tremendous amount of energy. So at 400 calories per day, I was curious to know whether or not that was like a bright light, like a 16-watt LED light bulb, or is it more like a 5-watt pen light? And so what I thought would be fun to do is to just go ahead and do this conversion to illustrate conversions between different kinds of energy units. So what we're going to do is think about it like this. I have 400, gosh darn it, 400 calories, right? And I have per day, right, like this. Now I'm trying to get it into watts. Now a watt is a joule per second. So that what that means is this top value, oh my goodness, this top value needs to be converted to lowercase calorie because I have, now I want to change the slide and it won't let me. There we go. I have a relationship between the uppercase and the lowercase calorie that I talked about on this slide. Right, one calorie is 1,000 small calories or kcals. And then once I get it to the calorie, right, this lowercase calorie, I can get it over to joules. So calorie will take us to joules. And then the day is a fairly straightforward like time conversion, right? There's 20. I'll get it into hours. I'll get that into minutes. And then I'll get that into seconds. So I'm going to go ahead and do the calculation here. I'll take, well, actually, why don't you try to do the calculation, and then when you restart the video, I'll just have it all set up and you can see how it's done. But really, make an effort to do this. It's one of the few energy conversion problems I'll do. Okay, so let me walk you through the calculation. But the good news is you're like a bright light bulb, regardless of what you're doing, it turns out. This first segment of the calculation is simply to convert from calories, uppercase, to joules. Okay. The second part of the conversion uses the idea of 24 hours in a day, 60 minutes in an hour, 60 seconds in a minute. You saw some of that when I did the hour to seconds conversion, right? That's just to get this to cancel out properly. Right? So that's to hours, that's to minutes, and this is to seconds. And now I have do all the math on the calculator. I checked it a couple times. 19.37 joules per second. Now the sig figs on this is a little bit questionable. Like the 20% was like a 2 sig fig number. The 2,000 calories might have been a 2 sig fig. It's not, it just depends on who you are. So ballparking, I'm just going to say 2 sig figs is probably sufficiently good for this calculation. And basically your brain, just when you're resting, is like a pretty bright bulb. Like the 16 watt LED is about the same brightness as 100 watt sort of incandescent, if I remember right. It's pretty bright. Okay, so 19 watt would be a little bit even brighter than that.